Welcome to another session of microwave engineering. Today we'll be dealing with stub matching. This is another form of impedance matching technique in which we are going to use distributed matching, meaning your final design will be not in the form of lumped elements, inductor and capacitor, but will be in the form of microstrip lines. They can be either connected as in the form of series connection or in parallel connection. This is stub matching, and in this stub matching we are going to use only short circuit or open circuit stub, which will be informed in the consequent designs which we are going to see. In the first problem, which we have taken from Poser book, we are starting with shunt matching. The question given is for a load impedance ZL equal to 60 minus J 80 ohms, design two single stub short circuit shunt tuning networks to match this load to a 50 ohm line. The designs for doing this is, first we plot impedance ZL, so 60 minus J 80 is given. The characteristic impedance is given 50 ohms. So when you take normalization of this, it becomes 60 upon 50 minus J 80 upon 50. Answer comes out to be 1.2 minus J 1.6. So first you are supposed to plot 1.2 on the resistance line, which is a horizontal line, and after that plot the susceptance value as plot the impedance value as minus J 1.6, which is a capacitance. You will plot that point. After that, we will be plotting the VSWR circle. How do we plot a VSWR circle? We take the center of the compass at the unity gain point, that is 1, and take the radius of this plotted point as 1.2 minus J 1.6 and plot the circle. After plotting the circle, we will be plotting the admittance. How do we plot the admittance? We take a scale and draw a straight line passing through the plotted impedance point, passing through the center of the Smith chart, and that line is taken outside the Smith chart. The point opposite to the plotted impedance is called as admittance point. Why are we trying to find the admittance is because in this problem they have given it is a shunt tuning network. If they wouldn't have given shunt tuning network, we would have continued by plotted impedance value, provided they would have given it as a series tuning network, which we will be doing it in the next problem. This is a shunt tuning network, hence we are supposed to find the admittance point. I hope you all are clear with it. After that, we will be highlighting the unity gain circle. I hope you remember that is a dark circle which we have, the solid circle which we have on the right hand side, whose the circumference of the circle always passes through that one point, the center point, the match point. When you find that when you are plotting the unity gain circle and the VSWR circle, you find both the circles are intersecting at 2 points. So in the clockwise direction, you will be selecting the nearest 2 points. After the selection of the points, you are supposed to find the distances. Now, how do you find the distances? Because in this stub matching, first of all, we need to find out that where are you going to place the stub. That is called as position of the stub. Position of the stub in our problem will be designated as D, the distance of position of stub. So this distance, there can be two possible solutions for each stub position. So D1 over here will be found out by the point, and D2 will be another point that will be solved. To start with the design, as shown in the previous slide, we are supposed to first plot ZL. So how do we plot the ZL point? It is given 1.2 minus J 1.6. 1.2 meaning we are going to take it from, this is your center point 1. So 1.2 will come approximately here. I'll just highlight the circle. And then minus J 1.6. Minus means capacitance, if you remember. So this thing will go down. I'm here. So this is 1, right? This line is 1. So it becomes 1.2, 1.4, 1.6. Why am I looking down? Because it was given in the problem as minus J 1.6. And I'm taking ZL given as 60 minus J 80 ohm divided by 50 ohm, it becomes 1.2 minus G 1.6. So I'm taking minus G 1.6. I'm just taking this point to find out exact setting. So this is the exact setting. Now, since it is given shunt configuration, we are supposed to find in terms of admittance. How do you find admittance? Is you keep the compass at the center of the Smith chart. This is the center of the Smith chart. Okay. You keep the compass center here. Take the radius. The radius can be exactly this point, right? You keep the center of the compass here. Radius can be this line up to the plotted ZL point. ZL point, and plot the circle. And plot the circle. While you plot, you can see it looks something like this. This is how it looks when you plot the circle. Your ZL point is already plotted here, and this is your YL point. What is this YL point? YL point is the admittance points. How did they draw this? Admittance point is they have taken the scale, drawn a straight line passing through the ZL point, center of Smith chart, and also the admittance point. This is how you plot the admittance point. Now, to continue with the design, after plotting the admittance point, we are supposed to know the unity gain circle. You know the unity gain circle, right? The unity gain circle over here is this one. I told you before too. This is the unity gain circle. I'm just highlighting it for your reference. Otherwise, it's not required. Normally, unity gain circle is always dark. So I'm just making it dark for you all. The unity gain circle. Now you will see that your VSWR circle and unity gain circle are intersecting at 2 points. Now you will take in clockwise direction. In clockwise means this way. In clockwise direction, that point which is nearer to this admittance point as Y1 and the other point will be taken as Y2. So you can see your unity gain circle and the VSWR circle both are intersecting at 2 points. Y1, can you see this? Y1 and Y2. Y1 and Y2. So this becomes our points Y1 and Y2. Why did I take this point as Y1? Because this is the point in clockwise direction nearest to YL. After that, the second point is always named Y2. This is how we normally allocate the points. Once the points are given, we are supposed to find D1 and D2. Now what does D1 and D2 means? D1 means the position of the stub. Every point has got two possible solutions. If you remember lumped element matching also, we had two possible solutions. Same way, for single stub also, we will be having two possible solutions. So how do we find it is, you are supposed to draw a straight line passing through the point Y1. Can you see over here? This line is already drawn. A straight line passing through the point, and this line has to be taken outside the Smith chart because whatever answers you're going to tell us is going to be always in terms of lambda. If you remember, the entire circumference of Smith chart was 0.5 lambda. So what we're going to do is that when you're taking it outside the lambdas, you can see over here, you can just let me know the value of Y1 in terms of lambda. So what will be the value of Y1 in terms of lambda is, you can just look over here, that value will come approximately, I'm telling you this one. I'm asking you this point. This point. Can you all see it? This point, that will come approximately 0.175 lambda. Sorry, 1 second. It's coming as 0.175 lambda. This point is 0.175 lambda. This is D1. And what is the value of lambda for the point YL? Can you all tell me? That will be over here. You can see in your Smith chart if you're drawing along with me. Then you can see in your Smith chart that value is coming out to be as, I'm talking about this point. This point. This point. Because this is along the YL in terms of lambda. That is 0.064 lambda. So D1 is calculated as greater minus smaller. That is, in clockwise direction, 0.175 lambda minus 0.64 lambda. that I have given in the notes that it is 0.11 lambda. So you will get the point D1 as it has been shown over here. You can see over here it is marked here like this. It is 0.175 minus 0.064. So I'm just marking it for you all. This is going to be your D1. Your D1. And this is your D1. Similarly, can you find D2 for me? Very simple. You have to first draw a straight line passing through the center of Smith chart, passing through this Y2 point and outside the Smith chart. So here already the line is drawn. Can you tell me what will be the point for that? It will be 0.0. So this value is 0.347. You will get approximately value. Nothing to worry. If it is 0.45, 0.345, something like that, it's fine. So you're getting 0.347 lambda. So how will you find D2 now? D2 will be again your distance between, in clockwise direction you should go. That is from distance between the position of this Y2 and, sorry, 1 minute. Yeah. So you will take the distance as, I'm just marking it over here only, so it becomes easier for everybody. Just have to go in this way. So this becomes your D2. So the value will be D2 will be equal to 0.347 lambda minus 0.064 lambda. That value comes out to be as the value comes out to be as 0.261 lambda. I have given this in notes. 0.26 lambda. This is the value you're going to get for D2. So in this way, you are going to find for D1 and D2. Now, how do we find for L1 and L2? Now, what does L1 and L2 mean? L1 means the length of transmission line used as short circuit stub. Same way, L2 means the length of transmission line used as the second possible solution for short circuit stub. To find L1 and L2, how do we proceed is something like this. For this, first of all, you need to find out the complex conjugate value of Y1 and Y2. Now, what will be the value of Y1? Can you tell me the impedance value of this Y1? So this value is marked Y1 up. So what will you tell me that value? How much will you get Y1? You just have to take the susceptance value up. I'm just marking it for you all, so it might be easy. When you mark this up, you will find this susceptance value is coming out to be as plus J1.43. It is coming plus J1.43. Now you are supposed to take complex conjugate of the susceptance value. Now why are we doing this to find the line? Normally what happens is that when you connect a stub means when you're connecting a portion of transmission line in a direction parallel to the existing transmission line, the VSWR of that value has to come 1. The VSWR value is coming as 1 means the normalized impedance at that point has to be 1. Normalized impedance has to be 1 means the real value is 1. So impedance, the impedance value has to be equal to 0. To make the impedance value equal to 0, in this case, you can also check that this Y1, when you are marking, you have got plus J1.43. So the real value of this over here, you have all seen it is 1. And this, you have to cancel it out. So what do I do? Take a complex conjugate of it. So this plus J1.43 has to be marked down as minus J1.43. That will come approximately here. Continuing with the design, I am going to explain how to get L1 and L2 for the above design. We already know how to find D1 and D2. To find L1 and L2, what we are doing over here is that we will first find the point L1. So for that, we know the point Y1. Find the complex conjugate of this point. The value of this y1 has been found out as plus j 1.43. Taking complex conjugate of this point, it becomes minus j 1.43. So minus j 1.43 comes over here, and then we draw a straight line passing through the center outside, and this line becomes L1. So the value of this L1, when you note, it comes out to be as 0.347 lambda. 0.4347 lambda. Please note, we are trying to design a short circuit type of shunt configuration. So since it is a short circuit, how do we find the distance is something like this. We always take your short circuit point as here on the left hand side where your impedance is equal to 0. We find this distance from the short circuit termination. So this is from here, the entire up till here, it is always 0.25 lambda. I hope you know that. I have told you before also. The entire circumference is always 0.5 lambda. The half will be 0.25 lambda. So this 0.25 lambda and the point up till here is coming out to be 0.347 lambda. So we take this entire thing as if you ask me how much distance has it traveled, we always subtract this 0.347 lambda minus 0.25 lambda, and the net value you get as 0.097 lambda. So the value of L1, we say when it is short circuit termination, has to be 0.097 lambda. What does 0.097 designate is that total lambda distance is 0.347 lambda. This 0.347 lambda subtracted that 0.25 lambda, you get the value as 0.097 lambda. Please note, if you cannot remember this, we just remember as if this value is greater than 0.25 lambda, we need to subtract. What happens if it is greater? If it is less than 0.25 lambda, we will check it out. Now suppose we are getting the point y2. Y2 will be minus j 1.43. The complex conjugate of this will be plus j 1.43. Here a line is already drawn for L2. If you see in terms of lambda, that value comes out to be 0.154 lambda, this one. But this value is less than 0.25 lambda. We add 0.25 lambda to it, and your final answer comes out to be as 0.404 lambda. In reality, what this means is that we are trying to find out the distance from the short circuit termination which is happening. Okay, so this value is coming out to be 0.404 lambda. So we are trying to design a short circuit termination over here. Suppose the same problem they would have asked with open circuit, then what you had done is you would not have subtracted nor added 0.25 lambda to your answers. Whatever answer you had got, for example L1, you had got the answer as 0.347 lambda, you would have kept as it is. You would not have subtracted 0.25 lambda from it. Same applies to L2. L2 would have been 0.154 lambda. You would not have added 0.25 lambda to it. That is only difference if the same question is asked with open circuit tuning network. I hope you have understood. Let us see at the final circuit diagram. I've written the open important points for you all so that you remember it. This is the final circuit diagram. For L1, this was the point I was telling you. This is the D1. This is the stub matching which we are having. You are having here D1. This is the L1, length of the transmission line, which has been used as stub. This is a position where the stub is kept. There is no need of putting this 0.995. You can just leave it. The important point over here is a 50 ohm matching network is here. The D has to be marked and L has to be marked. Only D and L. Rest all you can ignore it. Please ignore it. That is computer used using some CAD software they have solved it. You need not do all these things. You can just mark this 50 ohms at not point, the D and the L. With this your design gets over. So I have given you one more